Okay, so we are going to walk our way through the 5 organic reactions that we really need to discuss for this class. So there's addition reactions, oxidation reduction, also called redox reactions, substitution, esterification, polymerization. There are thousands of others we are not going to touch. These are the 5 that we are really going to focus on. So when we look at addition reactions, these must involve a double or a triple bond. They have to either have an alkene or an alkyne. As the name suggests, it involves adding a compound to that double bond. Sometimes we use a thing called a catalyst that's used to speed up the reaction, and this would be written over the arrow. So in these reactions, there's sometimes a mechanism. That mechanism would visually show you the steps the molecule follows in order for it to complete the reaction. So let's look at an example. Now, this is what we call a stepwise reaction. That means it's going to be occurring in steps. So the hydrochloric acid is going to break into hydrogen and chlorine in that solution. It's an ionic compound. The hydrogen is acting as the metal, the chloride is the nonmetal. So the hydrogen ion is going to attack the double bond. Well, why do you think it's going to attack the double bond? Well, that double bond has electrons. And opposites attract. That hydrogen is positively charged. It wants an electron. So this is going to cause the electrons in that double bond to drop out, and they're going to bond with the hydrogen. That's going to leave the other C that it is not bonded to slightly positive. So since that carbon is missing a bond, it is going to be slightly positive. Now it is highly unstable. This is known as a carbocation. This atom is going to react immediately. Anything that is negative, in this case that is chlorine, anything negative is going to go there. So that means that the new electrons for this bond are coming from the chlorine atom because the carbon doesn't have extra electrons to spare. So all of our addition reactions are going to occur this way. There's going to be something positive, we call that the electrophile, that is going to attack the double bond. We have that carbocation form. Then something negative attacks the carbocation. So a common question here is, why do we call the positive atom an electrophile? That is basically because it's an electron-loving or an electron-seeking molecule or atom, and so since the opposites attract, that's what we call it. So we can add a number of substances to these double or triple bonds. Halogens can be added if we have a UV light catalyst, and the mechanism is going to follow the same pattern. We are going to have an attack of the double bond by something positive. We form the carbocation, we attack the carbocation by something negative. The UV catalyst, what it does is it breaks that chlorine, which is a diatomic, into 2 chlorine ions, one positive, one negative. So eventually, both of the halogens are added to the double bond. That increases the boiling point of the compound. Well, why do you think that is? What's the information we know about halogens? So if you think about halogens, what we know about their electronegativity, that is what's going to be happening to helping increase that boiling point. So this is what we use when we are solidifying hydrocarbons. This is how we make the PVC pipes used in your house. So what about if I wanted to do bromine? Similar thing. So when we are working with alcohols, alcohols are going to be made from water and an alkene or an alkyne. So we can break that water into the hydrogen ion and the hydroxide using that double bond. So the hydrogen ion is going to attack first, the carbocation forms, the hydroxide ion is then going to attack that carbocation. And so that overall effect is we are going to end up with an alcohol. So what else could we use? Well, we could use a catalyst. We could add hydrogen using a catalyst. We can break that double bond in order to allow us to add 2 hydrogens. This also is going to be raising the boiling point. This is a hydrogenated. This would be how we make margarine and other fats. We create them using a hydrogenation process. We add extra hydrogens into the system. So how do we do that? Well, that platinum atom is going to hold the hydrogen diatomic into place. The hydrogens are then going to split and it's going to attack that double bond, very similar to the other addition reactions. So when we're looking at oils and fats, there's a lot of double and triple bonds. Some of these are broken, which is what we call partially hydrogenated. And so that's going to raise the boiling point slightly. If we continue and we eventually break all of them, it's going to be much, much more. So the physical state is going to be based on the amount of hydrogenation. So we are going to go from a liquid to a slightly thicker liquid to even perhaps a solid based on the amount of hydrogenation. So partial hydrogenation, we're breaking some of these double bonds. So here we have a saturated fatty acid. Every carbon is maxed out on the number of hydrogens he can hold. He's got his max bonds here, but everybody else, he's full. Then what's going to happen is that here we have a monounsaturated fatty acid. There's an extra bond here that could have held a hydrogen and it doesn't. If we're looking at a polyunsaturated fatty acid, we've got a couple of extra bonds here that could have held a hydrogen that aren't. So when we are looking at a partial hydrogenation, what that's going to do is that's going to change the texture of the fat and it creates something that's called a trans fatty acid, which is kind of bad for your health. So not only can alkenes undergo addition, alkynes can as well. So when we are looking at alkynes, similarly to what we just did, we're going to break that triple bond. We're going to add in, and then we can break that double bond, and we're going to add in. So eventually what we're doing is we're working our way down into all single bonds. So when we're talking an addition reaction, we are eliminating double or triple bonds and we are adding compounds. We are adding elements into that system. So kind of the question everybody wants to know is, does it matter what the carbon is attacking? Can I just go, I declare you to be the one we're attacking? Does it matter which carbon we're going to be attacked? If the molecule is symmetrical, it doesn't matter. However, there was a Russian scientist, Markov, who found that with things that are not symmetrical, it does matter. So here, if we are doing an addition reaction, the question becomes, will the hydrogen ion attack carbon 1 or carbon 2? So what Markov's rule states is that the carbocation will form on the more substituted carbon. Okay, that's kind of fancy speak. So what exactly does that mean? That means we're going to go and look at these 2 spots where the carbocations can form, and we want to know which one is going to form. Well, the one that is the most stable. If it's unstable, then we need to stabilize it, and we're going to stabilize it by electrons. So nearby carbon-hydrogen bonds that have electrons will flow over in order to stabilize that carbocation, and we call this hyperconjugation. So if I look at what's going on, so if I'm looking at carbon 2, I've got 1, 2, 3, 4 hydrogens that can come in and share and stabilize this carbon. If I'm looking at this one right here, I only have these 3, so I have less. So Markonov's rule states that the carbocation, or the positive carbon, is going to form on the atom that has more attached carbons. Therefore, it has more hyperconjugation for stability. We call that Markonov's rule. So that means that we're going to be looking at carbon 2. Carbon 2. Okay, so let's look at this reaction. So here we have hydrochloric acid reacting with this molecule. So what would we expect with this reaction? Would we expect something that looks like this? Why do you think so? So pause, think about this, and come back. So instead of that forming, we get something that looks like this. Why would we do that? The entire molecule is rearranging its form in order to cause a stable carbocation. We call this rearrangement of the carbocation. So that means that our methyl group is going to jump over and leave a place for that chlorine to come in. That chlorine is going to come in, and that is going to attach at carbon 2, not at carbon 3. So I'm going to pause here. What I want you guys to do is to make sure that you are working on your diagrams. You have 20 of your diagrams with the naming to make sure you have turned in by the beginning of next week. So there will be some questions coming out about these. Make sure you have taken notes because I will be checking those.